I'm Antonio Sala, and in this video we'll discuss some issues regarding the operating point selection in a complex process. We are going to discuss an idealistic air conditioning setup so we can understand without any complicated formula the main issues. This is a simplistic setup. In fact, setting the temperature of an air conditioning system in one room is kind of a simple setup, so I am not claiming that anyone in practice will use what I'm going to propose. I am just claiming that in complex industrial processes, the ideas we are putting forward in this video are actually needed in order to efficiently operate plants. In air conditioning of a small room, you just have the remote control and set the temperature without any computations with multicriteria optimization, as we are going to set up. But as I said, the emphasis here is explaining complicated stuff with a very simple process so that anyone can understand just by common sense. So, we will assume that we have heating, ventilation, air conditioning system. We will pose an air conditioning problem, summertime, in which we must balance power usage with respect to user comfort. So in this axis, we will say that the lower this y coordinate, we'll call it C, comfort related, the better comfort we will have. So this will be the most comfortable setup. And in here, we will have a setup which is uncomfortable, the most uncomfortable thing. So actually, when we go up, we are measuring this comfort. On the horizontal axis, we'll have power usage. So when we go towards the right, we will interpret this as requiring higher and higher power usage. So our optimal setup would be here, the most comfortable situation without any power usage. But of course, we will not be able to attain that. So we need to compare things in the middle, say this point 1 versus this point 2, to say which one is better. It's important to realize that these requirements are conflicting, in the sense that if it's summer and very hot outside, in order to get a better level of comfort, I will need a higher refrigerating power usage. So, as I said, this orange point will not be attainable. So let us discuss what comparing two different points in this diagram mean. Let us first start with an easy comparison. For instance, if I compare points 1 and 2 here, then this comparison is easy because, point 2 has more discomfort and more power cost. So if we could achieve 1 and instead we decided to aim for 2 as our operating point, this would be nonsense, because point 1 wins over point 2 in both criteria, more comfort and less power usage. So in this case, comparison is easy. In multicriteria optimization jargon, if I drew a vertical line and a horizontal line starting in point 1, then this horizontal line to the right means same comfort, higher power cost. Then of course it's nonsense preferring anything in the gray horizontal line to point 1. Analogously, the vertical line indicates less comfort for the same power usage. So if we have design alternatives in which operating point is selected in this vertical line, those design alternatives are again nonsense. With the same power usage, I can get 1 instead of these other ones, which are less comfortable to my users. So I will not choose any design alternative above 1 in the vertical line, or at the right hand side of 1 in this horizontal line, or as we discussed with 2, we would not choose anything in this region that I strike out in red. These solutions in the red region are called dominated choices, dominated solutions, in the sense that if 1 is a valid design option for my operating point, then I would not choose any operating point in the red zone, even if it's technologically feasible, because, okay, everybody understands that it would be nonsense choosing 2 instead of 1. So this is what these conflicting requirements mean, and the concept of dominated choices in a multi-criterion decision problem. So we will now discuss how to compare other things. For instance, we will now have these new points 1 and 2. Okay, without extra assumptions, these 2 points cannot be compared, because if I plot the points that 1 dominates and I plot the points that 2 dominates, then 1 is not dominated by 2 and vice versa. 2 is not dominated by 1. So they cannot be ranked with this common sense idea that we used when we were discussing these 2 points before. So we just now need to introduce additional considerations into the equation. These need to be user-defined. So for instance, we may say that an intermediate level of discomfort and no power use may be equally preferable to an intermediate level of power usage and the maximum possible comfort of my users. And somehow I would be able to draw a line in between, and this line will be a line of equal preference. This would indicate that if my user is faced in choosing between 1, 2, or any other technological option in this curve, then my user would not express any particular preference. In a complex setup, we will solve the operating point selection by some kind of optimization, and then this line will be like an equal cost, being cost kind of function of the discomfort level and the power usage level. And this blue line would be like a level set in a mountain, let's say, denoting equal cost. Then if I denote such a cost as capital J, this line may have, let's say, J equal 3. I may have this J equal 2, J equal 1, and J equal 0 would be, maximum comfort, minimum power. And of course, I may have J equal 4, J equal 7, or whatever I might decide. As I said when I was presenting this video, it's unlikely that in an actual problem of setting a reference temperature, I am using this kind of optimizations and dominated solutions in multicriteria stuff, okay? But if you understand this, then you are ready to understand what's going on in a complex industrial problem in which you have lots of quality of your final product, costs of energy, costs of raw materials, pollutants in your waste, etc., that need to be combined in order to set the most efficient operating point of your complex process. So something similar to this will be set up. This cost should verify a couple of properties in order to actually code what a user would expect in this particular problem. The first one is that this slope must be negative, because imagine that I had as a fraction of the equal preference line with positive slope. Whatever it does on the rest, we will just think locally like here. In this case, this point here would preclude choosing as equally preferable the dominated solutions. So choosing this point 2 over point 1 would be nonsense. So setting a mathematical problem for this application in which I have a first, third quadrant slope would be nonsense according to this common sense criteria that I would never prefer 2 over 1. So this is why it's a must that we have a negative slope here. The other advisable but not mathematically required is that J, this cost, is a convex function. What is a convex function? Well, For a mathematician, it's that if I draw an imaginary straight line between points 1 and 2, then if I consider an intermediate point, let me call it x, then this cost is convex if the cost of point x, being x, some interpolating coefficient alpha times 0.1 plus 1 minus alpha times 0.2, with alpha between 0 and 1. If alpha is 0, we are at 0.2. If alpha is 1, we are at 0.1. And this alpha is 0.5, then we are halfway between them. So the function is convex if this cost is less or equal than alpha cost of 0.1 plus 1 minus alpha times the cost of 0.2. As 0.1 and 0.2 are in this equal preference, equal cost blue level set, and this was 3. So alpha and minus alpha cancel out, and this is 3. So that means that any point in the pink line will have a cost lower than 3. So this is kind of the shape we are drawing here. You know, the closer I am to the origin, let's say, then the lower the cost. So indeed, the points in here, if we imagine this in 3D, it's kind of a valley with the deepest point in the valley being here, and these points have a cost lower than 3. So this kind of behavior is called a convex cost function. This is not formally required from a mathematical point of view, but it will be convenient for later optimization setups, and also it has an intuitive interpretation which is in accordance to common sense. Indeed, if we consider an alternative scenario in which the equal cost, equal preference were like here, so points in the line will have a higher cost than the points 1 and 2, then if we look at the slope, in this case, at point 1, we are saying that we are willing to trade off a small amount of extra power only if we obtain a high comfort for my users. So for instance, this point, which has a lower slope, will not be preferable to those on the blue line. What does this mean? Well, still nothing until I compare with the other point. Around here, the slope indicates that when I am close to point 2, I am willing to trade off a very small level of comfort improvement, this vertical thing, by a large energy consumption, horizontal arrow. Why this is not common sense? Because, well, you know, in this kind of problem, at least, in here I'm saying that when my users feel bad and I am not using power, then I am somehow being power conscious. Then your user would say, come on, you have installed the air conditioning for something. It's kind of nonsense to tell us that you are not going to power it on because it's too expensive. On the other side, in point 2, users feel very well and I am using a high amount of power, and then in point 2 I am saying that, wow, okay, no problem. Increase the power a lot, even if you are feeling very well, so your increase in comfort will be negligible. That's nonsense. I mean, when my users are feeling more or less well, my emphasis should be in avoiding wasting power. So this too is kind of nonsense. In the same way, in point 1, this is less understandable than this kind of slope. When my users are feeling very badly, I wish to turn on the air conditioning so that they improve their comfort. And of course, I know that using air conditioning is expensive and I need to use power to satisfy them. So, in summary, this kind of slope, indicating this kind of convex cost function, in this particular problem seems more reasonable than this other kind of a slope, because in here I am prioritizing power when comfort is bad, and in here I am prioritizing comfort when power use is high. So this is somehow opposite to what a sensible user would wish from my system, which is prioritizing comfort when comfort is bad, and prioritizing power usage when comfort is good and power usage is already high. So this is why we should propose kind of convex cost function in order to have a sensible setup that a user would understand, that it replicates what he would do if he had to think on it. How can we actually get this convex cost function for my operating point optimization? Well, if this is the C coordinate and this is the P coordinate, this line will be J equal a linear function of C and P with alpha 1 and alpha 2 being positive. But I can also get a convex function with, let's say, the square, so the level sets will have the form of an ellipse. I can remove the square here, so I will have a parabola, or equally, if I have here, I will have another type of parabola. All of them verifying this convexity if these coefficients are positive. Of course, these kind of nitty-gritty details are not usually what the end user, the one who pays, will tell me how to do. These things that translate the common sense user criteria to numbers for optimization problems will be usually a task to be carried out by the engineers who are programming this kind of plant optimization. It's important to note that these plant optimizations, in many cases, are the lion's share with respect to the global efficiency and profitability of the plant. Myself, as a control engineer, I'm used to think that, tuning a regulator so that a gain is 7 or 8 or 6 is a very important thing, but maybe the money is in these optimizations on the power usage and temperatures to pursue instead of the time constant of the temperature control. This is how we will end up with our cost function. Negative slope, for sure, mathematically required, given our conflicting requirements, and convex function, because in this problem at least, it's kind of closer to common sense on how I would start with a preference for comfort and I will end up with a preference for power saving. So good. We need to introduce the actual physical plant to see which operating point is actually achievable with this physical plant and my particular technology used to cool it. So I might have an outside temperature of say 32 centigrades and my plant have a comfort versus power like this. Comfort or discomfort depends on many things. Inner temperature, moisture content of the air, how people are stressed, radiation temperature felt by people in windows, and it also depends on psychology, culture, sex. So in fact there are kind of studies where they set up called predictive mean vote on this stuff, but okay, setting the ideal temperature, moisture, whatever things in an office in which 200 people are going to work is kind of complicated. I am not a specialist over these things, so I will just forget. And for simplicity, I will imagine that this comfort is somehow related to temperature. So this will be no power and 32 centigrades in the inside of my office building. And these may be the temperature levels associated to each level of comfort. If I am at 26 centigrades, let's say in a summer day, and I keep increasing power usage and cooling even more, then people start getting discomfort because the office is too cold. So if I lower to, let's say, 25, 24, 23 centigrades, then people will be shivering of cold if they are, dressed in shorts. So in a particular problem, this can be the temperature profile with respect to comfort, And of course, one easy solution would be setting the operating point here if I am just prioritizing maximum comfort. This part of the plot here will be, of course, dominated by this point, so I would never choose an operating point in this region. The other extreme point would be prioritizing energy consumptions, so avoiding switching the air conditioning at every moment, so I will have people sweating in the office, but zero cost. And of course, the sensible criteria, given all the previous discussion, would be choosing this intermediate point in which I have 28 centigrades as desired temperature, and it's a trade-off between power usage and comfort. If I lower the temperature, then I would increase too much power usage according to my cost function. And if I lower power use, then I would increase too much temperature and discomfort according to this convex criteria. So my choice of operating point in this setup will be this 28 centigrades. Of course, as I said, I am not doing this kind of multi-criteria optimization when I am setting the temperature in my office. I just have the remote and set whatever temperature I wish. But if I am deciding which temperature and moisture levels and things like that in an industry with 300 workers, then it's better to think on this stuff seriously with an expert in air conditioning and in human behaviors, etc. So it's better to think on that than just letting anyone fiddle with the temperature of the whole factory at will. This multi-criteria optimization effort is meant for complex use cases, air conditioning for 100 people or more, or when we are, in a chemical factory or whatever, optimizing a lot of conflicting things. But at least with this simplified setup, we understood what a cost function means, what dominated solutions are, and things about the slope of the equal preference curves and convexity of the cost function. So this is it. Thanks for watching.